Yeah. So up until now, whatever we have yet studied, we were talking, let's say, about X, or we were, let's say, talking about Y. And here this thing denotes the number of claims, let's say, and sometimes it would also be the, oh, that's the same. So it could also be, the amount of claims. So up until now, we tried to study one particular random variable, and we said that, I care about the mean of this X, I care about the variance of this Y, and I want to see what happens to, let's say, the aggregate claim amount. So we defined this thing as X1 plus X2 and so on up until, let's say, Xn. So let's say if you're looking at the aggregate claim amount over a month period, what would we have here as an either 30 or 31, right? I mean, again, forget about the February issue. But yeah, let us say, suppose that we have observed the number of claims. So let us say my X1 here represents the number of claims within a particular day. And that is how, let's say, I figure out the total number of claims that I have incurred within a month. And again, if I'm looking at the amount of claim, I could do the same thing with Y1 and get basically the aggregate claim amount over the month period. So whatever we are doing, let's say when we are adding up these X1, X2, and Xn's, what are we observing? We observe X1, we observe X2, and so on, so till Xn. So these are the random variables that we have observed over time, right? And again, what we also take into consideration is that this time is increasing in nature, it's not decreasing. So it's not that we are looking at, the sum of claims today, then yesterday, and then a day before that, and a day prior to that. No. So we're looking at the future claims, and why again? We try to see if there is some pattern, and we try to figure out its characteristics and the main features. And then basically it's going to help us to model and to predict what can we expect in future of the same particular variable that we're trying to model for. So now that when I'm trying to introduce stochastic processes to you guys, I think we have already worked with stochastic processes, but again, we have worked with stochastic process, if I say, and let me just, maybe before formally defining it, if I just say that a stochastic process will have two aspects. One, a time domain, and the other will be state space. So does anyone know what is a state space? Has anyone heard of this before? State space? Have you guys heard of this before? So again, state space is actually nothing new. It is just, you can simply say that it is all the values that your Y variable or your X variable can take. So whatever random variable you decide and the values that it is going to take is defined as state space. And whenever I'm talking about time domain, it is, there's no explanation required, I guess. It is just the time over which you're observing a particular random variable. So let us say you start observing the rain, okay? So how much rain you have observed over a particular set of years, let's say. So if for each year you will have some data, and whenever you're trying to measure things, let us say you have rain data from 2001, 2002, and so on till 2020 for Assam, okay? And now you will have some numbers here. So if I ask you guys to guess two things, what do you think is my time here? Is it discrete or is it continuous? What do you guys think? Can you guys hear me?
Yes, ma'am.
Yeah, all right. So what do you guys think is the time here? Like, is it discrete or is it continuous? So when I'm looking at the annual rainfall, so again, first is I have time, and then I have the rainfall in, let's say, mm or a centimeter. Then what do you guys think my time variable here would be?
Discrete.
Exactly, right? It will be discrete. Why do you think so? Okay, I don't want answer from you. I want answer from someone else. Do you agree? Is the time variable indeed discrete or is it continuous? What do other people think? Come on, I mean, I don't get why are you guys not answering this question? Can I at least have a hello from everyone just to check? Yeah, Vanshika, you wanted to say something?
Yeah, I think it should be discrete.
Okay, and why do you think it should be discrete?
Because even though if it's time, we consider like it as a discrete variable because we say like 1 minute or 1 hour or 1 day. We don't consider the nanoseconds and the microseconds. So maybe.
Okay, all right, all right. And here in this particular rainfall example, we see that, we have specifically considered years. So this is year one, year two, or let's say if you want to start from zero, this is year zero, year one, and so on, right? So you can specifically, whenever you're, let's say, trying to plot a graph, you can write the years here. So this will be 2001, 2002, 2003, and so on. So this will be time, and here you will have annual rainfall, let's say average, if you're looking at average annual rainfall, right? And you'll be plotting particular numbers here, right? Those will arrive, let's say, something like this. So let us say this is the data that you get. I mean, again, whenever we are looking at rainfall data, we expect it to possess some seasonal factors, right? So whenever we are looking at the monsoon time, the annual rainfall would actually be much more higher. But as and when we approach the winter and summers, the rainfall will decrease, right? So, okay, but again, whatever the numbers that I'm going to plot here, what do you guys think these are? Are these numbers discrete or are these numbers continuous in nature? So again, I'm talking about the average annual rainfall. So will that variable be discrete or continuous? And that is my question.
Still discrete, right?
Why do you think so, Isha?
Because we can point it out as as in a particular point of time.
Okay. So Isha thinks it is discrete. How many of the rest of you guys think and agree with Isha that it is discrete? Or does anyone believe that it is continuous? Or it can be continuous? Okay, so Isha just said that, if, because we can measure it in, let's say, numbers, it should be discrete. So let us go back to what we have yet studied. Let us say, we did see examples, right, where my X was measuring the claim amount that my insurance company will have, let's say, for a particular time period. And then we said that my X follows exponential distribution. So even though we know that claim amount is just going to be one particular number, We approximated x to what? To a continuous distribution which is exponential, right? Did we use a discrete distribution for claim amount? Even though we know there will be a particular value, 20,000, 30,000 or 23,000 for the claim amount that will be incurred. So what do you guys think this rainfall will be? Will it be discrete or will it be continuous, or can it be both? So I wouldn't say any answer is correct or incorrect here. It just, again, what matters is the way you present your argument in favor of the answer that you have written. So Isha said it should be discrete, and I want to know what do other people think about the same. And I'm not going to move forward until each of you guys answer, because I think this is really, I need participation from the class. Does anyone think this can be continuous? Yes or no? All right, I guess even I'm going to take a seat now. I have no idea why is no one answering today.
Even I think it will be discrete.
And why do you think it will be discrete, Savi?
Because ma'am, you're counting the amount of rainfall, right? So it is taking a particular value.
For example, let's say like 163 centimeter, 140 centimeter, right?
Yes.
So you think it's
yes,
going to take a value in particular number? All right. Thank you very much, Savi.
Ma'am, even I feel the same.
Even Anvaya feels the same. Okay. What about others?
Yes, ma'am, I feel the same, because suppose you are measuring the rainfall between 2 years, so we know the data between 2 years, right? So we know discrete value.
Okay. And what about the rest of you guys? I guess you left to hear from Shivani and Urjita. Urjita, did you just join?
Yes, ma'am.
Okay, so we are looking at the average annual rainfall example. And what I just said, that we have data over a period of times. So let's say I started off from 2001 to 2020, and I have the data of average annual rainfall in centimeters or in mm, anything. So I'm just trying to plot it here, and I want to know whether the variable on y-axis here, which is the average annual rainfall, is discrete or continuous. So I guess maximum of the people from here say that it should be discrete. I want to know what do you guys think about it.
Ma'am, I think...
I guess you're muted, Urjita. Yeah.
Sorry, yes, I think it should be continuous, because if we look at the rainfall, it can be anything between two ranges. Like, for example, if we take a maximum rainfall figure for like 100 mm, then 0 से 100 के बीच में the rainfall can be anything in the year. So the state's continuous.
Okay. So what do other people have to say about this? So Urjita believes that it should be continuous because of the very fact that if I'm, let's say, considering a range of 0 to 100, it can take any particular number between 0 and 100. Yes, Shivani. And from the people who just said that this should be discrete, why do you think, do you think Urjita's answer makes sense? Yes, Isha, Anvaya, Mihir, and Savri. I guess Vanshika.
Yes, ma'am, it makes sense.
Okay. So again, why do you think it makes sense?
like she said, that if we will always be measuring rainfall between some range, so it can take any value between that range. So we
Right,
can't.
and by any, exactly, and
But
by any value.
that
Yes.
value itself will be discrete, right?
Okay, good,
Exactly.
good. Okay, so Urjita, what do you have to say to this?
And ma'am, like usually when we see the rainfall statistics or anything, you do have a specific number. Like I don't believe I have seen, like for different places altogether there might be a range. But for one place specifically, we mostly have a specific number, right?
Okay, Urjita, what do you have to say to this, guys? So again, to those people who are saying that, because we observe a particular number, and that is the reason that the average annual rainfall should ideally be a discrete random variable. I just have one counter example to put forth. So up until now, we studied about, the claim amount, the aggregate claim amount, X, let's say. So I'm talking about only one claim amount, let's say. So X, a claim amount observed from a particular policy. And we know that the claim amount will be a particular number, right? Either 2, 3, I mean, in thousands or anything, right? So why did we use continuous distribution? So sometimes we said that my claim amount follows exponential. Sometimes we said it follows Weibull distribution. So these are what? These are continuous distributions, right? So why did we use continuous distributions even though we know for a fact the numbers will be, like specific number, right? So, I mean, is that explanation enough to conclude that this will be a discrete, I mean, this should ideally be a discrete random variable? Yes, Savri, what would you say to this?
Ma'am, like when we are taking the continuous distribution for those claim values, we are looking for the probability that that X is less than equal to or greater than equal to those particular claim amounts. We are not looking at X equal to, and that's why we take continuous. But here, if we know that like the average rainfall will be equal to, because we are calculating it, so it will be discrete, right?
Okay, so with the claim amounts, I mean, a person will come and will, let's say we are filling up the form for the claim amounts. I mean, we will still know, right, a particular value for the claim amount, that 20,000 is the claim incurred by so and so guy, right? And even with the average annual rainfall, so let us say, let us say I'm looking at future. So sometimes, so okay, I think we could still have an ongoing discussion about the same thing. But the point that I wanted you guys to, explicitly mention is that it really depends on the way we look at it. So none of you guys is wrong and none of you guys is correct every time. It just depends on the thing that you want to model in particular. So this average annual rainfall can either be discrete or be continuous. Again, but what makes much more sense in this case is for us to consider it in a continuous manner. And let me explain you guys why. So, okay, whenever I'm looking at this, even though I'm plotting this in dots, what do you see? I'm plotting this dot, so I can literally, plot this dot anywhere from here till here, right? So my annual rainfall could either be 99.9, it could either be 89.85, or it could either be 86, or it could either be 100. So for us, we are used to seeing, so whenever I talk about continuous, I'm used to seeing a line something like this. And now when I plotted some dots here, it kind of gives you an illusion maybe that this is something that might not be, a continuous variable on the y-axis. So again, whenever I'm looking at a process, the way I define a process to be either a continuous or discrete depends on both of these guys. So I have time domain, which can either be discrete or continuous, and then I have a state space, which can either be discrete and continuous. So we have these 4 possibilities and 4 combinations of time and state space that will give you various different kind of stochastic processes that we will be looking at. So let us see if I'm looking at this rainfall data. And if I have to guess, if I just have to say what is my average annual rainfall in 2001, it could be any of these numbers beyond this, but these are just an example set that I'm giving you guys. So it could be 89.85, it could be 99.9, right? And I can always plot it on this y-axis, either here or here or here, depending on what the actual number is. But let us take another example. So let us say I'm considering the number of claims that I incurred. So I know that I can only incur either 1 number of claim or 2 number of claim. There wouldn't exist anything such as 1.5 number of claims, right? So we know that the value can only be either 1 or 2 or 3 or 4. So I know that there are a certain set of values already predefined. So I can maybe see that, it spans from 0 till infinity. So I know that it will only take integer values like 0, 1, 2, 3, and so on. And 1.5 number of claims doesn't make any sense, right? So we see that the number of claims are follow discrete distribution. Sometimes we say it's Poisson, sometimes we can say it's something else as well. So negative binomial or anything else, geometric sometimes. But again, do you guys understand the way we see or check if a process, if a random variable is discrete or continuous? So do you guys understand why does it make much more sense to look at average annual rainfall as a continuous state space random variable?
Ma'am?
Yes, Isha?
So can we say that it is because it happens in a flow, like we are measuring it in a discrete way, but the process is happening in a flow. So like the rainfall, like if you're measuring it, it won't become like 100 mm at a point and then 101 immediately. There, like in between also it will be taking some values.
Yes, that is one of the reasons. What about the other guys? Do you understand?
Yes, ma'am.
Okay,
Yes,
so, okay, good. So I think a very famous example for any stochastic process would, okay, so let me just write a chart. Maybe what we can do is, we can define, let's say, something. So let's say I can write my time here, and I can write my state space here. Okay, and what I'm gonna say is that this can either be discrete or continuous, and so can this guy. So let us say I write discrete here, and I write continuous here. And again, I write discrete here, and I write continuous here. So out of these 4 boxes, which one do you think the rainfall example will fit in? Where should I be writing? Should I be writing this is 1, 2, let's say 3, and 4? Where should I be writing the rainfall example that we just discussed? I couldn't hear you. 2? Did you say 2?
Yeah, 2.
Exactly right. Because the state space that we were looking at was continuous and the times was discrete. So we were measuring time in years. And we know we can measure 1 year, 2 year, 3 year, or let's say if we were observing rainfall over a month, over let's say months, then we could also say that, 1 month, 2 months, 3 months, or let's say quarters, first quarter, second quarter, third quarter, and so on. And that is why, the annual rainfall example would fit into second category. But again, can you guys think of something where my time is also continuous? So my state space is continuous, and so is my time space. So is my time domain. What example can you think of in that particular case? So let us say there is something that you are measuring instantaneously, and that particular value is a continuous random variable in itself. Can you guys think of an example?
The age.
The age. That is actually a good example, right? So again, if you are measuring your age in terms of years, it could still classify as a discrete state space and maybe discrete time as well. But again, I think the age that Isha is considering is, let's say if you're measuring it in terms of days or something, you can probably, it kind of would make sense to model it as a continuous state space and in continuous time, because days in comparison to year would be a very minute thing. So again, there is no hard and fast rule to allow modeling of a particular random variable in a continuous state space or in a discrete state space. So what matters more is what suits best the purpose that you have at hand. So sometimes it's very easy for us to model anything in continuous, because let's say if we have a continuous state space, then we can use integration directly, and it's easier to use integration than to use summation most of the times. But again, I want more examples. Any more examples?
Will heart rate will be considered?
Yes. If you're exactly, you can, it's fine. Yes. Any more examples? Almost everything around you can be modeled as a stochastic process in either of these 4 categories. So I guess there should be no, dearth of examples that you guys can come up with. Okay, so can you guys come up with another example for this series? So where my time is still discrete and my state space is continuous. So, okay, any of you can give me examples for any of these 4 categories. I would accept it if your explanation is correct. Come on, I need more examples. I need you guys to think, look around yourself, look at indicators. It can be financial indicators, economic indicators. Heart rate was a really cool example. Age, cool example.
Ma'am, for the third one,
yes,
be the waiting time between 2 events.
Waiting time between 2 events. Oh, that was actually a very nice example. So I can say Yes. Can you explain that a bit, Vanshita?
Like for toll naka, if I consider, if I want to calculate the waiting time between like two cars entering, so the time would be continuous, but the event occurring, that is the cars that will be coming, that will be discrete, because obviously.
I mean, yeah, there can be one car, two car, right?
Yes.
That was a
Yes.
very good example. Yeah. So such examples, there is a theory, like probability theory, you have queuing theory. It goes like this queuing theory, and wherein you study pause processes. So all of these Ponza processes will exactly come under the third category, right? Where if you're looking at the where if you're looking at the waiting time, what you are measuring is time, right? And that time can be continuous. And the let's say the vehicle is, as in the example of Anshita, it's gonna pass through the toll. So those will be either one vehicle, two vehicles. You can count those vehicles, and that will be discrete state. So that was a very good example. Any other examples?
For the first category, GDP per annum.
GDP per annum. Okay, so Isha, if I want to measure GDP, what do you think it will be? Like GDP can take any number, right? Again, it can be 7.7. Sorry, if you're measuring the gross domestic product, it will be like a very high number, right? I was
Yeah,
talking
okay,
about
then population per year.
population per year would again be, so again, see, you can actually measure it using discrete as well. But again, it would be ideal to make it a continuous process, right? Because population can take so many numbers, right? It could vary a lot. So the ideal thing would be to, let's say, model population using a continuous distribution, like let's say normal distribution or something else, or maybe log gamma. So again, I wouldn't really, so this is actually a very difficult, this is the most trickiest to come up with an example for. But I guess if you guys keep thinking, so Isha, all the examples that you have yet mentioned would fit right in here, in second category, I would say. So the GDP example and the population would also fit in the second category here. Do you understand why?
Yes, because like it is a big number and there can be minor fluctuations in it.
Yeah, exactly. It wouldn't really, matter much if you have 19,000 and if you observe one more guy, so 19,001. So, that would be like negligible thing, right? So what matters is a big difference, and that is where the continuity. So a very basic property when we are looking at continuous things is that a probability that it would take a certain number doesn't matter, but the probability that it would be between a certain things, between a certain interval, that matters, right? So that is what would matter with population as well. Is it higher than 10,000 million, or is it more, or is it less, this particular number, or something like that? We wouldn't necessarily be interested if it is 10,000 or not. It's probably the answer is always going to be no, right? Because it certainly will not take a one particular value. That is at least not what we are interested in, even though it might take that particular value. Good. So any other examples? We have 7 students in the class and I only have like 1, 2, 3, 4. And Isha gave 2 more examples, but yeah, we still don't have enough examples from everyone. Come on. Mihir, haven't heard from you.
Speed of a vehicle for
Speed of a
fourth
vehicle.
category
Yes, that
will
is a
be
good
changing
example.
second and the speed will be increasing or decreasing like.
Exactly. Yeah. Good example. Shivani, are you there? I can maybe also write this as, GDP upon population. So it could actually become a certain like per capita GDP or something, a ratio.
Ma'am, for discrete and discrete example, we will have to think on a very small scale, right? Because anything that goes in large numbers can be converted into a continuous thing,
Yes,
right?
yes.
So something like number of patients per day in a hospital.
Something like number of patients per day in a hospital. So, okay, number of patients per day. Yeah, I would say I think that can be a really it is a nice example. So the number of patients that we'll have will be either 1, 2, 3, right? So it will be discrete. And again, the time domain that we're looking at, let's say is, it would also be discrete. But again, the only thing that I find here a bit tricky is, okay, I guess, I want to know, what do you guys think there can be a problem? So let us say, Isha,
Ma'am,
that, yes, Mihir?
what about salary of workers? Like salary will be fixed and the number of workers will be fixed for discrete and discrete.
Oh, okay. So again, one thing I should make clear is, don't try to think of only the variables. Try to think of the questions that you will be answering using that particular variable. So let us say you're talking about the salary of a particular worker. Will you be interested in this question? Let's say if, I mean, will I ever ask you such a question? Here is your salary 25,000? Will I ever ask you such a question? No, right? It doesn't really make sense. I might ask you a question here. Are you paid like more than 50,000 or are you paid less than a lakh or something? So again, whenever it comes to salary of a particular worker or average salary of all the workers in a company or something, it would still be ideal to use a continuous distribution, right? To measure the salary random variable. Even the time will be discrete. So yes, all of these examples that you guys are giving would actually classify as something that is known as time series. So let us say, even if, the very basic example of time series would be the stock market, right? So let us say you're observing a particular stock's price at the end of each day. So let us say you're observing the closing stock price of any particular share that you have bought, then you will plot it over time, right? And even though that particular stock price is going to take a certain number, we know that it would always be ideal to approximate it using a continuous state space. So because again, so what will help again is to think of the distributions that you will associate your random variable with. So again, just in the case of POSWA, what I was thinking is the waiting time between two events. So these events that will occur will be like either 1, 2, or 3, right? So that would be, and again here I would say a very good example was number of patients in a day. You can actually approximate a discrete thing here because until and unless it's a very busy hospital, I would say the number of patients, if you just classify it as the number of heart patients in a day, I think that would
Yeah,
not
so I think it would be better to specify here that it is a very small hospital or something
yeah.
like that, or a very specific thing.
Yeah, exactly.
But
Yeah.
wouldn't this example also belong to the third category? Because the
Third
patient
category.
can come in any time during the 24 hours. So we don't know when they come in, but we do know that, of course, the state space is discrete.
Yeah, I
However,
see.
if we specify the number of patients every hour that come in the hospital, then that may be classified as discrete time space, for example.
Exactly right. So the same example, we can mold it a bit. We can ask a different question, and the answer to that question would classify as something which is a third category type process, right? So let us say we are looking at the number of patients, that come in, let's say, a particular stipulated time period, or let us say we are, that would be discrete. But now let us say if we are looking at what time it takes for another patient to arrive, given that there is already one patient, right? So the inter-arrival time between patients. In hospital. So that would again, because we're looking at time, it would be continuous. We're looking at the inter-arrival time, it would be continuous. And because the number of patients is limited, we know it is going to take discrete values. So yeah, inter-arrival times. So waiting. Yes, Vanshika?
What about the outcome observed on each roll of die? Will that fall into discrete category?
Okay. So yeah, I would say so. Again, let us say, there cannot be only one die involved, right? Because that would just be one random variable. It is not a process then. So let us say you're rolling a die once every day for a month, and then you're looking at it, then that would be a discrete, right? Because the number that you're going to get on a particular die is going to take only numbers between 1 and 6, and the number of days you have is 30. So yeah.
And number of errors in a code for discrete and discrete.
Yes, number of errors in a code, exactly. So I guess now you guys have gotten the hang of this thing, and I guess now you guys can come up with a variety and a multiple of examples for this thing. So yes, in this particular chapters, the chapters that will be coming forth will be looking at something that classifies as this type 1 category. So a discrete and a discrete, and I'll explain you guys what that kind of model would be in terms of what an actuary might be able to handle well and is concerned mostly with. Then we'll start off with this category, then we will move to this third category, and we also have 2 chapters on time series. So we'll also be looking at this particular category as well. And this continuous, I would say, it's not really that difficult as well, but this is something that is part of, I don't know what that subject is, but it was CT8 previously. So there is something in CT8 called as Brownian motion, which will be measuring the stock price data instantaneously. So here, remember when I was trying to give you guys an example of the stock price, it was something like the closing stock price or adjusted closing price that I would be looking at for a particular stock at the end of the day. So I would get one value for one day, right? And if I want to model stock prices instantaneously, let's say if I'm trading, then I would have to be aware of the intraday trading, and let's say if you're doing intraday trading, so each second of the day also matters a lot, I would say. So you would fit that in here. So I can maybe see that Brownian motion would come under this category. So because it looks at the stock price data for each particular moment. All right. So again, now that we have classified this, so this is all the exclusive stochastic processes that you can ever have. So it would either be discrete or continuous, and time would either be discrete or continuous. And now it's just a matter of time that you will figure out how to model in each of these particular cases. So again, remember, so I'm not going to give you guys, I'm not going to write definitions here, and definitions might come up in the exam. So I would encourage you all to, go through this chapter again to just look at the definitions and everything. But my value here is in giving you guys the intuition behind those definitions and what matters the most. So again, I'm trying to read the definition of a stochastic process from your book. So it says that a stochastic process is a model for a time-dependent random phenomenon. So again, remember all these, I mean, we didn't know in prior what rainfall would be. We didn't know what the value of GDP will be, right? We don't know what the value of stock price will be. So again, the very nature of the process is random. And that is the reason why we have to model it. Otherwise, if it's predictable, then I guess there is no point. So again, you can either have a look at stochastic processes or you will have deterministic kind of processes. So whenever I'm talking about deterministic processes, those processes would be something that I know for sure what's going to happen next. So that is like fixed. So there is no random effect in there. But again, whenever we are looking at processes where we do not know for sure what's going to happen, it would classify as a stochastic process. And again, it depends on time. So it varies across time. And that is why we would usually have, let us say we are looking at the time series example, you will have time on the x-axis and a particular variable that interests you on the y-axis. So generally, if you look at the graphs of stock prices, you would see that if you're looking at the graphs of macroeconomic indicators, you would see that, GDP plotted over the years. Usually we don't look at GDP, we look at the GDP growth rate. That matters much. So sometimes you look at the absolute numbers, sometimes you would look at the difference between them, and sometimes you might actually look at the percentage change from one particular variable to the another variable. So again, with respect to stock prices, what happens is, whenever I think I might have mentioned this previously, but I didn't really go in that much of depth, but we will study why is it easier for us as statisticians to model the stock return instead of a particular stock price. Oh, and I'll tell you guys the intuition behind it, or maybe I can just say it now. So I guess you guys have enough background. So let us say I'm modeling this stock price. So here I have the time and here I have stock price, okay? So this is my stock price. So if I say that the stock price today is something, let's say 100, what is the chance of me observing the similar stock's price as, let's say, something, cannot go back in time. So what is the chance of me observing a price here and a price right here the next day? So which one of these do you think is more likely to happen? Anyone? I think the ideal guess would just be this, right? I mean, the stock prices will not really fluctuate this much until and unless there is some catastrophe or until unless there is some shift in the investor's perception or something else going on, the other factors. But again, we see that, a stock price can either go this way or maybe this way. But having such a steep decrease in the price is very, very unlikely. So sometimes what happens is, even though, let's say, this is unlikely, there is a chance that this might still happen. Let's say you were looking at 2007. So yes, there was a sharp decline in the stock prices and the stocks plummeted for almost each and every company you might think of. But again, if you have a look at
that is like extreme value theory, ma'am, right?
Yeah. It is indeed like extreme value theory. So in extreme value, you would only consider, let's say, the stock prices over here. I mean, you would not consider this normal box. You would either consider this or this. But again, your most concern area is this. So you would only consider this to model. I mean, these would be your data values, right? Okay. But again, whenever I'm looking at stock price, and this is, let's say, my time, the stock price data is usually something like this. Okay. I mean, it doesn't vary much. And it is either increasing. So you see a particular trend, right? This stock's price is increasing on an average, right? Otherwise, sometimes you also look at, let's say now if you're looking at the return of a particular stock price, does anyone know how do we define a return of a stock price? Let us say today's price is as 0 and tomorrow's price is as 1. So what would be the return earned on this particular stock within this particular day? It will be S1 minus S0 divided by What should I write here? Should I write S0 or
S0.
S0, right? Because that is the base that we're comparing upon. So I want to see what increase there has been in the price from S0. So S1 minus S0 is the difference, and S0 is the base that we started off with. And then if you multiply it by 100, you would get things in percentage terms or for the return on a particular stock. So if you try to plot return, you will get, something like this. I mean, there's not really much trend going on there sometimes. So return can be anything, I mean, in numbers. So sometimes what happens is we define a particular type of processes which are stationary processes. So whenever I'm talking about a stationary process, what does the word stationary usually mean in English? Like it's a stable sort of something, right? It doesn't move from a particular, it doesn't move from its place. So whenever I'm talking about stationary process in terms of statistics, there is a particular definition attached to it. So I'm looking at, let's say, to look at its actual statistical definition, it would say that, the joint distribution of some random variables will be identical over a particular time period. And you don't necessarily have to know it by now, but whenever you will study the chapter time series, you will understand what exactly stationary time series means. But again, in terms of the discrete processes that we will be studying now, so as of now, we'll be looking at either this processes or these processes. So here we are looking at a discrete state space, right? So stationary would mean, so let us say, let us say you shop at Zara, okay? So Isha shops at Zara, and what I want to see is, if at all there is a sale in H&M, will Isha shift to H&M? So what I'm looking at is, let's say I have discrete, so okay, maybe I can plot a matrix sort of or something with number of companies here, Zara, H&M, I don't know any more companies. But yeah, we can basically plot more and more companies here and more companies there, same. And we can see how many customers were with Zara the prior day, the prior year. So let us say we're looking at 2019. So the customers with Zara in 2019 and the customers with Zara in 2020. The customers who were shopping at H&M in 2019 and now let's say they're shopping at Zara in 2020. So we'll have these number of customers, right? So what we will be plotting, so we'll maybe, try to use continuous discrete process here. So the number of companies I have will be discrete, but the number of customers I would have would follow in a way some sort of a continuous distribution, right? But let us say now I look at the number of increase. I mean, how many, so let us see if I'm looking at the percentage of people who used to shop at Zara, and I'm looking at how many percentage of those people would still be shopping at Zara. So that would be a number, let's say between 0 and 100, right? So somewhere, I mean, you could say that you can, in a way, use a discrete thing for those percentages. But again, not always it would be beneficial for you to use a discrete thing there. And I mean, such are the cases that we will be looking at. And sometimes we can actually fit that example right in this case as well. But again, not every time it would be beneficial. It depends on the kind of question that you're asking. So again, not every process will be as easy for us to model as the other process. So there are certain kinds of processes which are very easy for us to model as statisticians, and we will describe what properties those processes possess in terms of statistics. So when I was talking about stationary process, I meant that, a process which would, to be technically correct, I'm talking about a weakly stationary. So in that case, I assume that, the mean is constant, the variance is constant over time, and the covariance only depends on time difference. So it doesn't depend on where I start from. So I guess a very good example to give you guys a picture of a difference between a stationary and a non-stationary would be to look at cricket. So let us say I am looking at, the number of, okay, we can actually have a look at the dice example as well. the dice rolled, okay? So let us say I define a random variable S here. This is the sum total of dice numbers observed. Okay, so again, I'm looking at the sum of the numbers that I have yet observed on a particular dice. So let us say I'm looking at first x1. The dice roll could either give me numbers like this, 4, 5, 6, right? x2, another day I will again get the same set, and so on till the end of the month, right? So now if I'm plotting this, so now let's say if I'm plotting this variable S here, it is always going to increase in nature, right? Because there is no negative number here. And what I'm doing is I'm looking at the sum total of dice numbers observed. So let us say here I observed 2, here I would let's say observe 1, here let's say I observed again 3, here let's say I observed 3. So the numbers would be increasing. I mean, the sum total of the numbers that I have observed on dice would be increasing in nature, right? So is the mean constant over here? So what I mean by is the mean constant. So generally what you do is, even, I mean, this technique is most often used in stock markets as well, but let us have a look at it using a dice example. So let us say this is 1, 2, 3, 4, 5, 6, 7, 8, okay? And we have some numbers here. So when I'm saying that my mean is not constant over time here, what do I mean is, let us say I take my time between 1 and 2. What will be my mean? Let's say somewhere here. I take my time 2 and 3, my mean is somewhere here. 3 and 4, my mean is somewhere here, right? Or let us say I look at 1 to 3, then my mean would be somewhere here. 2 to 4, then my mean would be somewhere there, here, then my mean would be somewhere here, right? So I know that my mean is increasing in nature, right? And similarly, if you have a look at this process here, which is stock return, I mean, the mean would be somewhere here for every time, right? So the mean is kind of constant, whatever time you look at, and the variance will be measured by the deviation from the mean, right? So it also kind of remains constant. But again, let us say if you are looking at a process which is something like this, and if you try to measure its variance, you might, so sometimes there is an increase, sometimes there is a decrease that you see over time. So sometimes what happens is, as in when you move forward in time, the volatility might decrease or the volatility might increase in general. So those will be the cases where the modeling would be very, very difficult. So here, let us say I'm talking about the mean now. So my x1 plus x2, let us say I observed here 2, 1, 3, 4, 6, and so on up until let's say 3. So if I'm adding up these numbers, it's certainly going to increase, right? So my S will take value from 1 to what? What is the maximum value that my S can take here? Anyone? Can you tell me the
6
maximum?
into 30.
Exactly right. It will be 180. 6 into 30. That is if you observe a number 6 on each and every die roll every single day. So that would be the maximum value that your S can take. So now, if you look at the actual event, it takes values from 1 to 6. But the variable that you are interested in is sum of the total. So that takes values from 1 to 180 and its distribution keeps changing. So let us say now what I do is I plot the numbers here. Okay, 1, 2, 3, 4, 5, and 6. And now what I'm looking
And
at.
the range will begin from 30, right? How can it be 1?
Oh yeah, sorry. Very good observation. It should begin from 30, right? So that is the minimum thing that you can observe. 1 times 30. Yes, it would be 30. Good. So yeah, it will always be between 30 and 180, right? So now when I'm plotting this particular graph, what I'm looking at is how many number of times I'm likely to observe a value of 1. How many number of times I will observe a value of 3. how much likely it is that I'm going to observe a value of 6. So if let's say I'm looking at a 2-day period, the number would be something like this. If let's say I'm looking at a 3-day period, or if let's say I'm looking at these over a month, because now these dice numbers have a uniform chance of occurring, right? So each of these numbers is likely to be observed. You will get something like this. But I mean, so I would say so this would be something which is easier to model, right? Because each of these values will be likely to occur, and you know that, 1, 2, 3, and if you are looking at the average value, average sum that you might expect would be like, 1 times 1 upon 6 and so on. So it would just be 1 by 6 times 1 plus 2 plus so on, so till 6, right? So that would be your average number that you would expect from a particular dice throw. And in a similar manner, you can calculate average for any number of days. So if you are looking at it for a month, you would just get something like this. So I would say that is the average, and it's really easy for you to look at because each of these numbers is equally likely to be observed. And the very reason it is because 1, 2, 3, 6 are numbers in the dice, and we are talking about an unbiased dice throw here. So that's good. And now let's say if this were the example of a cricket game, then we know that playing a 6 every single time is much more unlikely, right? So you would have observed, let's say, 2 runs or 3 runs much more times than you would observe a 6 on a particular ball, right? So I'm not taking into consideration the possibility where you can actually have more than 6 runs on a particular ball. But yeah, I'm just looking for, so let us say we have like a 5-over match and we are throwing 30 balls. So you can have one particular score for each particular ball. So now we know that taking a 1 run or a 2 run is much more probable than taking a 6 run on one particular ball, right? And again, it depends on so many factors. The batsman that's playing, the bowler that's bowling, the field, and the weather sometimes as well. So yeah, I mean, it really matters a lot and it varies a lot. So if you're looking at something like that, then you would be confused, like how to even model this. Because not every time you will have each of the data, and sometimes a model which is too complex might not serve the purpose, and its cost might even exceed the value that the model brings to the table. But again, here what happens is your probability is not the same here, not the same here, not the same here, not the same here. Because the batsman who was, let's say, batting at this first ball might not be the same batsman who is batting at this 30th ball as well. So whenever you have some data, or whenever, let's say, you have some questions that you are trying to answer, not always you will get data in a manner that is much, much easier for a statistician to process. So we will try to see how can we convert something which is not easier to model into something which is easier to model. And that we will study in the chapter time series. And let us say now that we are looking at, discrete cases, it's really not that difficult. So again, a very common example. So, okay, I should maybe just, give you guys the name. So a very common example that we will be studying for this particular case is of a Markov chain. Has anyone heard of Markov before? Oh, and here you would be studying something which is like a Markov jump process. So this is just another example. So as of now, we'll be studying about Markov chain in the next chapter as well. But the most common example in terms of insurance that you have, where you have a state space which is discrete as well as the time that is discrete, is of, let's say, a model which goes by the name of no discount model. So let us say that there are 3 possible discounts that are possible within an insurance company. So It could either be 0% or 25% or 40%. So these are three various discounts that a company offers to its policyholders. And what happens is they decide based on a policyholder's claim which type of discount they will be classified for. So let us say a policyholder would start, they can start at any of these discount rates, again, depending on their characteristics and everything else. But what happens is, let us say there is a claim observed from a particular policyholder in a particular year. So they will be downgraded to, let's say if they were starting at 25%, then they would be downgraded to 0%. Or let's say if they were at 0%, then there's nothing below that, so they will remain at 0%. Or let's say if they were starting at 40% and they incur a claim, then they will be downgraded to 25%. So the condition is that, let us say if you incur a claim, then you will be downgraded to a lower level of discount, or if there is nothing to go down from, then you will stay at the same level of discount. And let us say if there is no claim incurred within a year, then you would move up the ladder. So let us say if you were at 25% discount and you did not incur any claim during that year, then you would move to 40% discount level the next day. So let us say I have an insurance company which in such a manner decides the percentage discount that they have to offer to their policyholders. So this sometimes is, this is a very common example. So again, if you would look at the Moody ratings and these credit ratings of these credit rating companies, they have, AAA, AA, B, C, such kind of ratings for bonds. So a bond could either be a AAA today and then it could directly, be B tomorrow, or whether let's say a bond was B today, then it could actually be a AA tomorrow as well. So there are different possibilities that you do see. And within the insurance industry, this is something that we are looking at. And again, the time that we are looking at, let's say, is year now, right? So more often in stochastic processes, you denote these. So these are your three possible state spaces. So state space is denoted by S. And you can choose between either does make much more sense to denote it by T, but that would, T as a small subscript, you would be using it. So again, if I'm looking at the years, it could be taking values from 0, 1, 2, and so on up until 4. Sorry. So this grid, what happens is